Started. Okay, today we're very happy to have Kenji Fukushima to give us his seminar. And Kenji actually, we had overlap when we both at Brookhaven.
Yes.
And he got PhD in 2002 and from Tokyo University. Then he went to MIT as postdoc, and then went to Brookhaven, Riken in 2005. When I also was there as postdoc in 2007, both of us actually left Brookhaven, and he went back to Japan and took a position to Kyoto University and actually came to Berkeley. So when we had overlap at Brookhaven, he's doing Hawaiian dense matter. I'm doing spin physics. We didn't have much of the overlap physics, but we know each other. Actually, we meet almost like very often for conference, workshop, and some social gathering as well, because we're both postdocs at Brookhaven. So after Tokyo University, he went to also Keio University, and finally he moved to Tokyo University in 2013. He has been there almost 10 years now. And Kenji, without doubt, is a really expert on the quark-gluon plasma, in particular for the phase diagram QCD. He had a couple of original calculation for the QCD phase diagram and from NGL model and any other non-probability method. And today he's going to talk about a very interesting topic, and think also kind of continue with what he has been doing in the last 10 or 20 years. And it will be very interesting between nuclear quark matter and astrophysics implication and so on. Kenji, it's all yours, please.
Okay. Thank you very much for a very kind introduction, Fan. I'm very happy to see the face of my old friend. So today I'm going to talk about my recent work. Actually, my new paper appeared just yesterday, and so I would really appreciate your feedback. So if you have any comment or criticism, whatever, please don't hesitate to tell me anything. Okay, so essentially my talk is about the possibility to see the quark matter signal from the gravitational waves. So how to find the quark matter. But the motivation, of course, comes from the difficulty in dense QCD. As you know, the dense QCD is a very challenging subject, and so if you Google it, there are many phase diagrams. Of course, a GSI version and the Brookhaven version and well-known version that you must be very familiar. And my version here and my different version is also found here. And there are so many possibilities, like for example, the inhomogeneous phase like this, or some exotic pattern of chiral symmetry breaking, including some chance, some possibility of QCD critical point and the color superconductivity, etc. But unfortunately, all these fine details are very much model dependent, and so nothing is established yet. Well, and of course, that difficulty comes from the fact that there is no Monte Carlo simulation. The first principle calculation is very difficult. And the part additive QCD, of course, works, but it is not so successful. It partially works, as I will explain later. And so of course, a resummation program is necessary, and that is also possible, but still there are some uncertainty. But as I will emphasize later, the PQCD calculation is very powerful, and it gives a very useful constraint. So even though the uncertainty is large, there is a very useful way to use the PQCD output. And as I already told you, there are many model calculations like NJL, as Fan mentioned. And many years ago or decades ago, I was working using the NJL model to work out the phase structure involving the color superconductivity, but everything is model dependent, and depends on some uncontrollable parameters. That is model parameters. So they may depend on their density or temperature, but such dependence nobody knows. Well, and there are many interesting things, so if you go to a higher density, like for example, the liquid gas phase transition of nuclear matter, that is already a very well-known concept in nuclear physics, and also the QCD critical point, as I said. And so you must be, some of you must be more familiar to this subject than I am. But so this kind of a situation is very, very different if you go to the neutron star environment. That is because the isospin contents is very different. So essentially in heavy ion collision, you are investigating the symmetric nuclear matter. Symmetric means the symmetric between protons and neutrons. So the isospin density is not so large. But if you go to the neutron star environment, because of the Coulomb interaction and the charge neutrality, the neutron star matter is dominated by neutrons. And so you have a lot of isospin asymmetry. And then, as you see from this plot, this is actually some schematic plot of one particle energy. Then you see that there is a minimum here if the asymmetry is 0. That is a delta. The parameter delta is 0, then you can have such a minimum. And this minimum corresponds to the saturation density. And this is the point where you can find a self-bound nuclear system. And if you have such a self-bound system of fermions, you always have first-order phase transition. And this is the physics to have liquid gas phase transition. That is the first-order phase transition in nuclear physics. Okay, but if you go to a neutron-rich situation, there is no such minimum, and so the neutron matter is actually very continuous if you go to a higher and higher density, and there is no first-order phase transition. That is quite well known. So the phase structure and the nature of the phase transition is very different if you go to a neutron star physics. So in that sense, actually, I'm going to talk about the crossover scenario without any phase transition between nuclear matter and quark matter, but it does not exclude the possibility to have first order phase transition in heavy ion collision situation. Anyway, so this is a remark. Okay, now let me go to the discussion about the equation of state for neutron stars. So the equation of state is the most important physics information when you think about the structure of neutron stars. And then, so the question is, what is equation of state? And that is the relation between the pressure and the energy density, or the pressure and the density, rest mass density. But anyway, the point is, you have to solve the balance equation between the gravitational force and the pressure. So if you consider the compact star, for example, the compact star is a self-bound system. As I told you, if you consider the nuclear system, then the neutron-rich matter is no longer a self-bound system. But if the system size becomes larger and larger, thanks to the gravitational force, the system eventually becomes self-bound. And so this gravitational force should be sustained by the pressure. And so the balance equation is as simple as this one. The pressure gradient gives you the force, the outward force. And that should be the same as the gravitational force, that is the inward force. Okay, this is the balance equation or the hydrostatic equation, right? And this M, the mass, is of course the total mass. And once energy density is given, then the total mass is just the integrated quantity over the space. Okay, integrated quantity of the energy density over the space. So that's it. Okay, there are two equations. And of course, this hydrostatic condition is a Newtonian equation. That should be understandable for everyone. But of course, this must be generalized to the general relativistic description. And so there are several corrections. So this epsilon, okay, so up to this point, this expression is completely the same, right? But here, 1 plus blah blah. And this blah blah is just the general relativistic corrections. But the structure is almost the same, right? And this generalized equation is called the Tolman-Oppenheimer-Volkoff equation, or abbreviated as a T of equation, okay? So you must solve this differential equation and also the differential equation in terms of the mass and the energy density. But one condition is still missing, and that is the equation of state. Okay, you must know the relation between pressure and the energy density. Okay, this information is absolutely necessary to solve this coupled equations. And so, so once this relation between the pressure and the energy density, that is called the equation of state, EOS. Once the EOS is given, then you can solve everything, okay? I mean, if the initial condition is given at 0 at the center of the system, R equals 0, R is the radial distance, okay? Then there is a still unfixed parameter that is the energy density or the pressure at the center. That is the maximum value of the energy density or the pressure. And once this value is given, then you can just integrate these differential equations. And when the pressure becomes 0, that is a condition to find the surface of the system. And so from this point, the radius is fixed, and the radius of the star is now denoted by capital R. Okay, and in such a way, the capital R is found, and once capital R is fixed, the total mass is simply the mass of the star. So in this way, the M and R both are given as a function of this free parameter, the maximum value of the pressure. Okay, and so you can actually draw a curve, M and R. Okay, and that is nothing but the MR relation. And from the observation, you can constrain the equation of state, okay? And so this is the summary. So this picture is a summary of what we know about the equation of state. As I told you, the equation of state is the pressure, the relation between pressure and energy density. And of course, there are several available information from the observation already. And so for example, this green one is some astrophysical constraint coupled with some theoretical computation, the chiral effective theory, that is chiral perturbation theory. And so, so far, the uncertainty is not so small, but so this dotted one is some representative of a nuclear calculation, which is called the APR. So this is theoretical computation. But because this theoretical computation is based on the nuclear picture, oh, yes, yes, please. Peter, you have a question?
I didn't mean to interrupt, but actually go back to slide 5.
Slide 5, yes.
This epsilon max, you say it's a free parameter. Can it take
Yes.
literally any value? Or are there
Yes.
considerations from QCD where it's sort of limited from above?
Yeah, of course. So this is just a free parameter. But if this is too large, you cannot find the solution anymore. And so, yeah, in fact, so let me, the pen, yes, okay. So if you make, this is a radius R, and this is a mass, okay. And then, so this looks like this usually. And if epsilon max, P max become larger and larger, and eventually there's no solution or some turning point. And that is a maximum, maximum of the maximum. So you cannot go beyond this value. So there is some unphysical region, not really constrained by QCD itself, but there is some unphysical region. Okay.
What's unphysical? Is there some causality argument? What's being violated in the unphysical region?
The stability, some thermodynamic stability.
Okay.
So if okay, so that another chance is another possibility. Once this turns like this, okay, then of course this region is not really allowed, but this one is still possible. And such possibility is called the second family scenario. And there are several exotic scenarios about this. And so nobody knows the real maximum value of this epsilon max. Okay?
Okay, thank you.
Okay, thank you very much for the question. Okay, let me continue. What? How to I don't know how to okay. Okay, this is some computation about our knowledge about the equation of state. So this is so essentially from the observation, and also this NN, this red one is also from the observation, and this is actually our result using a machine learning inference. So with Koichi Murase and Yuki Fujimoto, I think that Yuki is in the audience. Okay, so if I say anything wrong, maybe Yuki can correct me. Okay. Well, anyway, so this red one is also based on the observation. Okay, the mass and radius of the neutron stars. There are several observations, and using that observational data, the equation of state is inferred, and that is actually the inverse problem. Okay, the TOV, as I told you, the TOV equation is easy to solve, but for that purpose, you must know the equation of state. And so from the given M and R distribution, you have to solve the inversely solve TOV to get the EOS. And this is an inverse problem. And machine learning is very useful for such kind of inverse problem. And so that is actually what we did with Yuki and Koichi. And then surprisingly, our result is very consistent with the nuclear empirical EOS, okay, the API, up to some point. And also, so this, the orange one is actually the PQCD result. So this uncertainty band, I will explain what is represented by this uncertainty band, but you may see that the PQCD result is very uncertain. And so you may have a first impression that PQCD is not really useful, but I must say that PQCD is very useful, even though you can find such huge uncertainty. Okay? And also recently with Yuki Fujimoto, we did some resummation calculation, and we found that this uncertainty is significantly reduced. But this is not so surprising. Okay, this is actually very natural. Okay, but so let me continue. Well, how you get uncertainty, let me explain that, okay? The PQCD, if you see the leading order PQCD calculation, that is just the free gas, ideal gas, okay? So this is just this if you have the massless particles, okay? For the moment, of course, there are some theoretical computations, including Quark mass, but to simplify my explanation, just let me focus on the massless situation, okay? Then, of course, the pressure is simply proportional to a chemical potential to the force power. And if you go to the next leading order, of course, you have some correction proportional to alpha s. And the next leading order is proportional to alpha s squared. But now the important point is, here you have the logarithmic term, okay? So even though alpha s itself may have some uncertainty, but if everything is proportional to a chemical potential to the force power, then, so this is conformal, right? And as long as conformality is kept, then the relation between pressure and the energy density is trivial, okay? So this is just the factor 1/3 and proportional to each other, and that's it. So there's no uncertainty. And the uncertainty comes from the breakdown of a conformality, and such conformal symmetry breaking comes from this logarithmic term, okay? So this is a source for the this uncertainty, okay? And so the uncertainty comes from next leading order, not next leading order, okay? But the question is, if you have such a term, if the chemical potential becomes larger and larger, as compared to some renormalization scale. So this log may become large. So this may sound very familiar to a PQCD expert like Fan. So if you go to the some kinetic regime of PQCD, of course, such a combination of log is everywhere. And as soon as you have log, large log, the log must be resummed. So that is a common story in PQCD. And that is, of course, the case here at finite density. So that you must do. And after doing such resummation, what you have is, of course, the running coupling constant. Okay. So the coupling constant should be replaced by running coupling constant. But then the question is, if this scale is chosen in such a way to be proportional to the chemical potential, then this chemical potential dependence can be canceled. Okay. But the question is, what should be some constant? Or what should be actually the constant part in the resummation? You can, of course, include arbitrary constant part in your resummation. Okay, not only log, but also some constant can be resummed. But what should be the ideal choice for such a constant part? That is the source of the uncertainty. Okay, and so in this notation, what should be the x for the most efficient resummation? And in the case of x equal 1, you find this. And if x equal 2, then you find this one. And if x is 4, you find this. So from this, you can see that x equal 1 is actually exceptional. Okay, x equal 2 and 4, the uncertainty is not so bad. But the only x equal 1 is terribly bad. But what is the reason why x equal 1 should not be excluded? That I never understand, okay? The people always show this kind of a huge uncertainty, but in my opinion, this is a sort of exaggeration of breakdown of PQCD. So probably this x equal 1 is simply a wrong choice. And in fact, if x equal 1, then for a given chemical potential, the argument of the running coupling constant is small, which means that this alpha s is large. And so the perturbative calculation is not really good. And so x equal 1 breakdown, this is very natural to understand, right? So anyway, this is, so the situation is not so bad as okay, so this is a bit misleading representation of the uncertainty. And so you may think that, oh, then the simple resummation may cure this situation, and that is the case, in fact. And that is we found, as I told you, this the blue one is actually the result after resummation, some simple resummation, the self-energy resummation we performed, and then x equal 1 and 2 and 4, they are not so far from each other, and so the convergence is not so bad. Okay, and from this computation, actually, you can see that this upper edge is very much favored because, as I told you, x equal 2 and 4, they stay together. Okay, so around here, and so the natural guess is that the genuine EOS should be located around here. Okay. And so, and that is, of course, supported by our resummed calculation. Okay, so I think that this is the most likely distribution of the equation, the EOS. Okay, but this is very interesting. Why? This is very interesting because, as I told you, this is the data-driven EOS. Okay, and data-driven EOS seems to be smoothly connected to the most likely distribution of PQCD EOS, right? But with some different slope. So there must be something here, or first of all, they could be smoothly connected without any discontinuity. That is already very interesting. And also the slope is different, okay? And this, so there should be some kind of a crossover here. And this crossover is a signal for the existence of a Quark matter. So this is a physical interpretation. And this picture was also emphasized by Alexei Brukera and Alexei Bronier, and our analysis is completely consistent with theirs. Okay. So, but before going to the gravitational wave analysis, let me emphasize this crossover picture is so natural and this is realistic. Okay, so of course this reality should be very familiar to the heavy ion collision people, because in heavy ion collision, the high density matter, the high temperature matter is investigated, and we already know from the lattice QCD there is no strict phase transition, but everything is a smooth crossover, and it is not so surprising to have the same situation at high density. But anyway, so if you see, so this is actually our favorite scenario, okay? So as I told you, there must be some crossover point here, and then change into the PQCD branch, and that is the region where you find Quark matter. And up to this point, the EOS is given by more empirical description, like a nuclear description or some data analysis. In fact, these gray bands, they represent the machine learning inference of experimental data together with Bayesian analysis of experimental data, and everything. The all analysis are consistent with each other. Okay, but still, the first order phase transition possibility is not really excluded, especially if the first order phase transition is located, if it takes place at very high density. Then the first order phase transition doesn't affect any observable quantity, and then the PQCD branch could be connected by very discontinuous jump like this. Okay, this is logically not really excluded, but I must say that this is a bit unlikely scenario, but still this is possible. And so I will explain why this continuity is expected and why this jump is still not really excluded from theory. Okay, there are several interesting scenarios or speculations from theory. Okay, so anyway, as I told you, we already know that the finite temperature situation is already a crossover, and then the hadron resonance gas model and PQCD, they both work in the intermediate region, and so there should be some overlap between the validity of the hadron resonance gas and the PQCD. And so such kind of a duality is a key to understand the crossover region. And so the same thing should happen in dense QCD. So there must be some dual region or some how to say overlapping region between nuclear description and partonic description. Okay, this is an important concept to understand the crossover or the duality between the two regimes. And that is actually nothing but the quakionic, okay, the so-called quakionic. Yeah, in fact, the quakionic is such theoretical picture of indistinguishability between baryonic matter and quark matter. Okay, if you have baryonic matter and quark matter, they cannot be distinguished if you take the large NC limit. That is actually the very important observation. And that situation is called the quakionic, named by these people, Larry McClellan and Rob Pisarski, as many of you may know. And so the argument is based on the observation of the pressure scaling if you go to the large NC. So of course, the quark pressure scales like NC because there are NC species of quarks. But the important point here is if you consider the baryonic matter, naively, you may think that the pressure should be of order 1, but that is not the case because the baryons interact very strongly, and that interaction comes from the quark exchange like this. And so from this, the system pressure scales like NC, just like the quark matter. And of course, this is very natural because here, through this exchange of a quark, the quark degrees of freedom is indirectly seen, okay? And so the matter is dominated by such interaction, and such interaction is some dual picture of quark degrees of freedom, okay, in the nuclear world. So this situation is now called a quakionic, And in terms of a more conventional nuclear picture, the nuclear-nuclear interaction and the three-body force, four-body force, and etc., many body force is mediated by the pion exchange. And such the endpoint interaction or higher point interactions, they become very stronger and stronger if you go to higher density. And it is known that all many body interactions become the same order if you go to the, for example, the density larger than twice of a nuclear saturation density. Then it is quite natural to expect so this situation, right? So this is actually the intuitive picture of realization of Quark deconfinement. Okay, so it is not so surprising to have a crossover from this picture of a deconfinement, right? So the change is not really the first order jump, but everything is continuous. But there's the stronger argument to support continuity between nuclear world and the Quark world. That is called a Quark-hadron continuity. And for this, you must have diquark condensate. But this is very interesting. So let me explain this. So if you have baryons, of course, the baryon is a bound state of 3 quarks. But approximately, you can regard this bound system as a bound system of diquark and quark. Okay, so it is known that this is approximately a good description of baryons. But then, if you have a good diquark here and one additional quark here, then the good diquark may have a condensate if you go to higher density. And once this is this becomes a condensation component, then the one quark is left here. And so this quark and this baryon, they must be dual to each other, right? In the presence of diquark condensate. And such continuity scenario is very well established. And especially if you consider the chiral symmetry breaking, of course, in the hadronic world, the chiral condensate QQ breaks chiral symmetry. But actually, if you have such a diquark condensate, the diquark condensates break chiral symmetry in a way completely the same as the hadronic world. Okay, the vector, only the vectorial component of the chiral symmetry is left unbroken. And so from this picture, it is also very natural to expect such continuity between the hadronic world and the high density world, where you can find chiral superconductivity. But then the interesting question is, okay, but there is actually a counter argument against this argument. Okay, yeah, you may think that, oh, now the crossover is so natural and there is no phase transition, everything is smoothly connected. But recently, there was a counter argument, and this is extremely interesting. So let me explain that. Okay, recently there is a big controversy, and this is an exciting development. So the physics problem is, okay, let me consider the following experiment. Okay, this is of course a thinking experiment, but suppose you have a big, huge bucket, okay, and the gravity force is acted, and then so here around the bottom you have very dense situation, and around the top you have dilute matter, and so there must be a some phase transitional change or crossover change from hadronic state to the Quark matter, okay? But suppose there's a continuity and they are smoothly connected, okay? And then let's rotate the bucket. Because the hadronic phase has a superfluid component, NN or the dibaryon, the condensation, then so if you rotate the superfluid, of course, you can have superfluid vortex, okay? Or some vortex lattice you can form. And then once such a vortex is created here, then of course, some corresponding vortex should exist also in the phase of a Quark matter, right? So the question is how they can be connected. So this problem was considered by these people, including myself, the Gordon and Mark and Tetsuo and Motoi. Okay, so we actually proposed a scenario of the vortex continuity. And here, so this is the hadronic vortex, and as I told you, this superfluid component is given by this dibaryon condensation, okay, the pairing of the baryon-baryon pairing. But of course, in the superconducting phase, the condensation component is dominated by diquarks. And so you can reorganize this dibaryon into 3 diquarks, okay? And then only one diquark component gives some some vortex configuration. Then they could be connected, okay? Some controversy comes from this fact that this corresponds to three diquarks. And if then naively, you might think that there must be three vortices because there are 3 different diquarks. Okay, but that is not really the case, because if you consider the angular momentum conservation, one vortex should correspond, one hadronic vortex should correspond to one diquark vortex, not 3 diquark vortex. Okay? But this is a bit strange description, because here, so this is not really a colored vortex, but here this is colored vortex. But anyway, mathematically, this kind of correspondence is possible. Okay. However, the Chairman and Sen and Yaffe, soon later proposed a different scenario. That is, so they computed the Wilson line circulating around the vortex. Okay, this test vortex means the hadronic vortex or this superconducting, the color superconducting vortex. Okay, and then they computed such the expectation value of the Wilson line, and they found that only in the superconducting phase, this is a colored vortex, as I told you, and so this is coupled to the gauge field, okay, the color gauge field, and from that vector potential of in color space, you can actually compute the Wilson line expectation value, and then you can find some non-trivial phase here. But of course, this phase doesn't exist in hadronic phase, because in hadronic phase, nothing is colored, and there is no such vector potential. Of course, there's no room to have such a phase. So the phase difference is found between these 2 phases. And so they concluded that there must be an interface, so there must be a phase transition, supposedly a first order phase transition. Okay. But later on, the Hirono and Tanizaki argued that in the infinite system, of course, such a global vortex is energetically prohibited. If you put such a global vortex, then the energy diverges, logarithmically diverges. But so this is, of course, the idealized theoretical argument. And of course, in real system, the system size is finite, and there must be some boundary condition, etc., etc. And so this is not so strong argument. But anyway, if the single vortex existence is prohibited, of course, this argument doesn't work. But still, this computation itself is completely correct. And so the existence of the first order phase transition is still under controversial arguments. And so everyone is still confused. But anyway, so this is the reason why the first order phase transition is still not really excluded. Okay, this is interesting, right? But anyway, for us, okay, for me, the crossover scenario is the most natural. And so I think that there must be something. For example, even in the hadronic phase, there might be some non-trivial phase, or in the color superconducting phase, this phase is averaged out, or there are several possibilities. But anyway, nobody knows the answer. Well, so this is anyway the theoretical underlying physics argument. Okay. Okay, now let me come to the main part of this talk. That is a gravitational wave signal. Okay. So, as some of you may know, this event GW 1708, the 17. So this is the most important event for us. So that is 2017 and August 17th. The gravitational wave was found, and from that, the mass, okay, the mass of the binary system can be estimated, and from that mass, the neutron star was concluded. They are not really the black hole merger, but it was concluded that this is the event of the binary neutron star merger. And fortunately, so this happened in such a distance as short as 40 megaparsec. So everyone considered that this must be a 100 or even 200 megaparsec, but we were very lucky because this was only a 40 megaparsec distance. And so for example, the kilonova was confirmed, and the kilonova is an electromagnetic event. And so there are many constraints coming from this event. So we were very lucky. And we are, of course, expecting more and more events coming in the future. But anyway, so far, it is known that the total mass is 2.75. And as I told you later, the kilonova is a very useful constraint to think about this event. And that is all possible because this event happened in such a short distance from us. Okay, anyway. So what is a gravitational wave? And so let me show you the typical example. Of course, you must have seen this kind of picture, the animation many times. But anyway, let me show you. This is a typical simulation result of the binary neutron star merger event. Okay, so this the stage is called the in spiral, and they don't touch yet, but so they lose energy and angular momentum, and so they touch, and so this is a merger point, and so this stage after the merger is called the post-merger. Okay, and then you see if the shape become almost axiosymmetric, then there is almost no gravitational wave emission anymore. But anyway, so okay, this is the situation. Okay, so from this in spiral phase, okay, so far only the in spiral state is seen. Okay, the post merger is a next generation challenge. As I told you, this was seen, but this is only in the in spiral stage. Okay, the post merger is not yet seen. Okay, but the next generation detector, the sensitivity is increased, and so the post merger is expected to be seen. Okay, and well. Okay, but from the in spiral state, the gravitation, the tidal deformability can be estimated, and from that you can already put some constraint to the possible EOS. And this is one example, analyzed by LIGO collaborations. And so this is anyway some distribution of the likely equation of state, the pressure and the rest mass density. And so they are all consistent. So far, they're consistent with some nuclear EOS. But here, in this region, the soft EOS is preferred from their analysis. And in fact, if you see the latest chiral EFT calculation, that is initial theoretical calculation. So in this region, I mean the low density region, the EOS was found to be very soft. As I told you, the APR and SLY, and there are several established nuclear EOS, empirical EOS, but in fact, the latest chiral EFT predicts even softer EOS. And so in this region, actually, the EOS seems to be very soft. And that seems to be consistent with the data analysis, okay, from the gravitational wave. And the PQCD constraint here, and this seems to be also very soft. Yes, Boka, what is your question?
These mergers, they are at finite temperature, right? So
yeah, after merger, yes, you are right.
Yeah, and these calculations are all 0 temperature. So how far can I trust this?
No. Okay, up to this point, 0 temperature, and this constraint comes from the tidal deformability, so 0 temperature.
Oh, okay, never mind. Yes.
Yeah, and of course, the after merger, of course, the finite temperature extension is necessary. And in fact, this is a little bit technical, so I will not explain this in this talk, but that is usually implemented by, this formula. And so there is a one parameter, which is called the thermal index. So this is based on some ideal gas picture. Okay, this is an approximation.
Yeah. Okay. All right.
Okay, thank you very much for the question. Okay, Now, what I want to emphasize here is that there are some ab initio calculations, but both predict very soft EOS. Okay, in this region very soft, and in this region very soft. And as I told you, okay, the x equal 1 gives you a huge uncertainty, but okay, such uncertainty is almost irrelevant because it is a direction to go to even softer. And if EOS becomes such soft, no chance to support massive neutron star. Okay, the existence of the neutron star with a mass as large as twice over solar mass, that is a fact. Okay, and to explain that fact, the EOS must be stiff enough. But if the PQCD is very soft, and if we require some smooth connection to the PQCD branch, then the EOS, such soft EOS, should be excluded. So, okay, this region of the uncertainty is completely irrelevant. Okay, so the EOS is, if you take such upper edge of the uncertainty, this is already very soft. Okay, so the only possible situation is something around this upper edge. Otherwise, the experimental data cannot be explained. So this means that this is very soft, this is very soft. So the some intermediate region must be very stiff. Okay, this some unknown region must be very stiff. So the soft, stiff, soft EOS should be the most likely EOS. Okay, and that is also supported by this machine learning inference and also the recent picture of a proteonic matter by Larry and Sanjay. And some people believe that there must be some peak structure in the sound of speed. So this is the speed of sound. Speed of sound. This is very different from the situation in heavy ion collision. Okay, usually in heavy ion collision, people are looking for the minimum in the speed of sound. But here, people believe that there should be some peak structure in the speed of sound. So the underlying physics is very interesting. That is still under discussion. But anyway, so okay, from this observation or from this analysis, it is obvious that there must be such peak. That is because this is soft. Okay, this slope is the speed of sound. Okay, and if the slope is small, then the equation of state is soft. Okay, very soft, and stiff means the sound velocity must increase here, and so there must be some peak structure. Okay. Anyway, so how to make the interpolation? We adapted the polytrope EOS, and the polytrope EOS is characterized by two parameters k and gamma here, and k is naturally determined once gamma is fixed from the continuity. Okay, so this is the crossover scenario, and this one is the first order phase transition scenario, and so here some stiffening density. As I told you, there must be some stiffening in the intermediate region, but from where you make such stiffening, that is still uncertain. And so there are two parameters, such as stiffening density and this polytropic index, adiabatic index. And we performed some analysis of the allowed regions of these parameters. And if you go to a larger and larger index, that is a stiff region. But of course, if this is a too stiff, the slope is too large. And then the speed of sound exceeds the speed of light. And so that is excluded from the causality. Okay. But as I told you, if the EOS is too soft, no chance to support the massive neutron stars. And so this gamma should be something around 3 point something to 6 or something, okay? Depending on the stiffening point. But the empirical EOS, the gamma is usually something around 3 and below 4. And so the conventional choice or some conservative choice is gamma is 3.5. That is our choice. Okay, this is consistent with some other empirical EOS. Okay, so this is the most favored value, and so that is so this picture is actually the situation when we chose gamma 3.5. Okay, and also the first order phase transition region. this first order point, P first order. So this is also almost excluded from the causality bound and also the massive neutron star bound. But around this region, there are still some allowed region, but this is nearly excluded. Anyway, so this is still not completely excluded, but this band is very narrow. And in the future, my belief is this could be also excluded from the future experimental data, more data from the in-spiral stage. But anyway, so far, so one cannot exclude such a possibility. Okay, and so that's the reason why we have this situation and this situation and make a comparison. Okay, and so we call this situation the scenario with crossover, and we call this situation without crossover. Okay, but this region is completely irrelevant because if the first order phase transition is located around here, then anyway, even in the merger event, no chance to have such a high density situation. So the existence of first order phase transition is almost irrelevant here. And then you may think that, oh, the first order phase transition around here, for example, that could be logically possible, but that is almost impossible, as I told you, from the PQCD constraint. The first order phase transition or the softening in the EOS is inconsistent with the existence of a massive neutron star. So in the future experimental data, from the future experimental data, I think that we can exclude such a possibility. Okay, that is the reason why we didn't think about such a possibility here. Anyway, so okay, so we adapt such a crossover situation and use the crossover EOS, and what happens? The difference is, okay, up to this point, okay, the merger, of course, nothing happens. Everything is just the same as the previous situation, but after merger, the density increases and eventually touches the crossover point. And then the equation of state becomes very soft, okay? And so once the PQCD branch is touched, then you have some instability and the gravitational collapse happens and the black hole formation is induced by the PQCD or the existence of a Quark matter. So this short lifetime is the signature for the Quark matter presence. Okay, this is our prediction. So this is a summary. So without crossover, some very hypermassive, transiently stable, but not really stable, hypermassive neutron star lives long. Okay, eventually it goes to a black hole, but the lifetime is very large. Okay, but if the EOS has such a Quark branch, that PQCD branch, such softening induces instability going into a black hole. And so this lifetime, from this lifetime, you can find how soft and when it happens. Okay, so from this experimental data, you can actually quantify the nature of the phase transition and the location of the onset of Quark matter in the future. That is our message. And let me mention there some comparison to the previous works. So so some people actually perform the simulation assuming some EOS, the Quark matter EOS, but with a strong first order phase transition, and they found essentially the same observation, qualitatively the same finding. That is the formation of a black hole in the case with the quarks. But actually the physics is almost the same. That is the phase transition, nature of the phase transition itself is not so important. Okay, the discontinuous jump or first order phase transition, that is not really important. But the important fact is the EOS becomes soft, and such softening induces the instability. And so the lifetime before the black hole formation, so that is actually the signature for the softening in EOS, and that can be interpreted as a Quark matter. So in that sense, our finding is completely consistent with their previous finding. But of course, the physics interpretation is different. Okay, they assumed a first order phase transition that could be almost excluded from other observation. But even in the case of crossover transition, continuous crossover, this black hole formation is very sensitive to the crossover. That is an important message we want to emphasize, okay? And also recently, some people reported some result not really consistent with ours. Okay, they say that their EOS is some Quark-hadron continuity, the crossover. This QHC means Quark-hadron crossover EOS. And they say that there is no black hole formation, but okay, so there are two misleading statements, I must say, or there's some confusing, sorry, the confusing statement. So first of all, their crossover is different from our crossover. Our crossover is more strict. Our crossover is a crossover to quark matter branch or PQCD EOS, but their crossover is a crossover to their model description in terms of quarks, okay, NGL model description, with very strong repulsive vector interaction. So this is almost the nuclear EOS, not really the PQCD EOS at all. Okay, so the meaning of crossover is very different, and also their thermal treatment is very different. Okay, as Volker asked me, there is a one parameter that is thermal index, and their value of thermal index is unphysically large. Okay, they overestimated the thermal pressure, and if the thermal pressure is large, of course, so you can have more pressure to support the hypermassive neutron star, and so the lifetime become larger. Okay, but this is because of such unphysical value of the thermal index. Okay, so that is the reason why they found some different result. Okay, for the crossover EOS. Anyway, okay, so this is essentially my last slide. So we already know many things. That is electromagnetic probe. We already know from the gravitational wave, the observation from GW 7008-17. And one of the most useful information is actually kilonova. And the kilonova is electromagnetic probe, as I told, the event, as I told you. And this is actually established, and the mass, the ejected mass, is also estimated like this. And this is actually a very important phenomena to explain the nuclear synthesis, and the heavy elements are created. And that evidence comes from this observation, and so in nuclear physics. So this is extremely important, and so the simulation must be consistent with this. And to explain this ejected mass, the mass around the black hole should be greater than this. Okay, otherwise the ejected mass cannot satisfy this value, right? The rest mass, the remaining mass must be greater than this mass. Okay, so that is important to check, and we checked that. Okay, after the formation of black hole, you can still have some mass distribution, and that mass can be computed. And so in the case of the equal mass merger, it is a bit marginal or some difficult to support this mass. Okay, but what we found was, in the case of asymmetric mass distribution, like this, for example, then it is quite easy to satisfy this condition. And so, but this also means that from this constraint, you can also put some useful constraint about the mass distribution, or actually this mass ratio could be precisely determined by the in-spiral observation in the future. Okay, so far for that event in the 2017, the mass ratio was not fixed. Okay, and so there is still some uncertainty. But in the future, such mass ratio could be fixed. And if such mass ratio is fixed, then together with this information of the ejected mass and the remaining mass, so the EOS could be further constrained. Okay, so that is actually the very important message we want to also emphasize here. Okay, so far nobody cared about this constraint. Okay, so this simulation and this simulation, they didn't say anything about this, but this is very, very important. Okay, and we found that anyway. So our crossover scenario is consistent with this very, the useful constraint. Okay, so here is my summary. So the gravitational waves from their post-merger stage, that is very useful probe to see their crossover transition to Quark matter. And you don't have to have first order phase transition, okay? So this is very nice, right? And the kilonova and the ejected mass, this is a very useful constraint. And so the future experimental data is really must be very useful to see such a transition to a Quark matter. Okay, thank you very much. Thank you very much for listening. Thank you.
Thank you very much, Kenji. It's very nice and interesting talk. We already had a couple of questions. Anybody from audience? Okay, Booker, go ahead.
So when I or is it possible to translate your finding of this crossover softening onto this plot which you generated and Larry and Sunshade? So the speed of sound is a function of, what is it, density, I think. So how would the two scenarios in this things look like on this plot? Is that possible?
So yes, their calculation is based on some physical picture.
But if I look at these variables, how would your crossover scenario and your non-crossover scenario look like? How would they, or could I then not distinguish?
Okay. So this is consistent with my crossover scenario. No crossover scenario does not have such behavior approaching the conformal limit. Okay.
No, but this could happen at higher densities, and then you never would see it, right?
Yeah. Then the first order phase transition means the speed of sound becomes 0. Yes. So it should look very different.
Yeah, but if your peak, instead of having this peak there, would be a wide plateau, and then it would dive down, let's say 2.5 or 3 or something like that, you couldn't distinguish. Then you wouldn't see this is you would have a crossover, but the crossover is so high densities that you never would see it in your. Is that a right statement?
So but after the merger, the around here can be actually reached. Okay, and then the softening means that the speed of sound becomes smaller, like this.
Yeah, understood.
Okay, and I see. So are you caring about the possibility of a first order phase transition?
No, what I'm talking about, so your non-crossover would simply mean a crossover at much higher density. Yet you can
yes.
Okay.
Yes, that simply means that they keep increasing, and so at some point, that is actually very, very high density. It suddenly jump into the 0.
Okay. All right. Okay. Good. Thank you.
Sophia?
Hi, can you hear me?
Hello. Yes. Hello.
Hi, Fukushima-san. Hello. Thank you very much for the nice presentation. I have a question regarding the differences between predictions from your crossover versus the QHC crossover, which implements the interpolation scheme, not a physical model. So as you already mentioned, in their higher density phase, they use this NGL model with vector interactions that usually give rise to a higher sound speed compared to the conformal limit. So my question is that does that have something to do with their EOS being slightly stiffer, even close to the maximum mass, so that the post-merger, the merger remnant is like probing different pressure range, and which might be closer to a purely without crossover version? How do you think about that possibility?
Yes, that is completely correct. So in fact, they don't have to have such a very stiff intermediate region, because this very stiff intermediate region is necessary because PQCD branch is very, very soft. But their EOS has, as you say, the NJL and very strong repulsive interaction, vector interaction. And so it is stiffer than PQCD prediction. And so actually the intermediate region is also different. And anyway, so that is more similar to the empirical EOS, nuclear EOS. Some continuous continuation of the empirical EOS, and that is actually, in their case, they adapted the Togashi EOS. Okay, the Togashi EOS up to some point. And then there are some change, but still this change is different from the behavior of PQCD. And that is actually the reason why the softening is weaker. And so the lifetime before black hole formation is longer. And on top of that, the thermal index is different. They took 2, but the thermal index here, you see the thermal index was taken to be 2, but if you see microscopic computation, for example, this one is a result from the chiral EFT, and you see there's no region, no density region where you can find as large as 2. Okay, it is around 1.7 or 1.5 or even smaller. And if thermal index is changed, lifetime significantly changes. So this lifetime sensitivity is very large.
And I think this thermal pressure component added to the merger simulation, which is necessary, of course, would probably impact the mass supported as well. For example, if you have more contribution from the thermal part, the collapsing timescale is probably smaller, right? I guess now even you guessing.
Yeah, the pressure, yes, the pressure have an extra contribution from the thermal pressure.
Yeah.
So yes, it can sustain against the gravitational collapse.
Yeah, okay, thanks for the clarification. So now I understand there are at least 2 factors that might contribute to the differences. And the first one is because of the US part closer to the merger density, and second is the different treatment of the thermal index. But potentially, I'm thinking about, for example, the observation of the collapsing timescale itself maybe can be used as an indicator of the true highest possible density, probable, right, in merger remnant that's sensitive to the stiffness or softness at the maximum mass, close to the maximum mass.
Yes,
it's interesting. No one has discussed about its distinguishability. Thank you so much.
Thank you.
Thank you. Any other question? Jim.
Oh, sorry. From the observational point of view, is one event enough?
Well, so probably you mean that, so this is just one simulation. And so you may, okay, I completely understand. Of course, this one event is not really enough. And so we should perform more systematic simulations corresponding to many different situations. And ideally, if the Bayesian analysis is possible, then that should be really fantastic. But this is really time-consuming simulation. So for one simulation, it takes 1 month. And so, of course, in the future, we really want to perform such a systematic survey. Yes, that is actually what we plan to do. Yes.
Okay, cool. Thank you.
Thank you very much, Kenji. And if no further question, let's thank Kenji again, and hope to see you maybe in the future at Berkeley.
Yeah. Okay. Yes.
Okay.
Thank you very much. Thank you.
Thank you.
Thank you.